Hi, everyone. Chebyshev's theorem and the 68, 95, 99.7% empirical rule help us understand how population values are clustered about the mean. Remember, the mean is an important flagpole that we plant in the data. And let's say that one standard deviation, sigma, is like a yardstick. It's like a basis for measurement. The idea is that we can't have too many values too far away from the mean. Both of these rules imply this. So this is one standard deviation. We cannot have large chunks of data that are too far away from the mean in terms of standard deviation. So for example, we can't have too much of the data that's more than 3 or 4 standard deviations away from the mean. So there has to be a certain clustering about the mean. It doesn't have to be close in like this, but you can't have huge proportions of clumps way out here and way out here. Now, a difference between these two rules is that Chebyshev's theorem applies to any distribution shape with finite standard deviation. So it applies to not just a bell curve, but also to something like this, or something like this, or something like this. Any sort of messed up shape, as long as you have finite standard deviation. And I'm not going to mess with you on infinite standard deviation in this class. So because Chebyshev's theorem applies to really any distribution shape, we say that it is by definition robust or distribution free. Now, what does this theorem say? Well, regardless of the distribution shape, at least 3/4 or at least 75% of the population values must lie within 2 standard deviations of the mean. So again, our flagpole is at the mean, mu. Here's 2 standard deviations above the mean, mu plus 2 sigma. I'll write it in red, mu plus 2 sigma. And here's 2 standard deviations below the mean, mu minus 2 sigma. At least 3/4 or 75% of the data will have to lie between these two goalposts. So it could be 75%, could be 80%. It could be actually all the data. That is possible, or all the population values. But it's guaranteed that at least 75% must lie within 2 standard deviations of the mean, which means that at most 25% can lie more than 2 standard deviations above the mean. At most 25% of the population values can lie more than 2 standard deviations away from the population mean. I'm assuming for now that we're dealing with population data. So again, we can't have too much too far out. We cannot have more than 1/4 or 25% of the data values or population values more than 2 standard deviations away from the mean. Again, the idea is that one standard deviation is like a yardstick or a basis for measurement. It could be 10 points on an exam. It could be 5 pounds when it comes to weights. It could be 42 light years in astronomy. Whatever one standard deviation is. Okay, so at least 3/4 or 75% of the population values have to lie within 2 standard deviations. Well, more than that, at least 8/9 or at least 89% of the population values must lie within 3 standard deviations of the mean. So again, here's our flagpole at the mean. So within 3 standard deviations of the mean, that means we're going from mu minus 3 sigma to mu plus 3 sigma. At least 89% of the population values must lie in here. It could be 89%, could be 95%, could be 99%, could be all the values. In fact, it wouldn't be shocking at all if all the values were within 3 standard deviations of the mean. And that means that at most 11% of the values can be more than 3 standard deviations away from the mean. Again, let's assume we're talking about population data, population standard deviation, population mean. So again, we can't have too much too far out. You can't have high proportions of data that are 4 or 5 standard deviations away from the mean. So that's Chebyshev's theorem, which applies to a variety of possible shapes. Next, we're going to talk about the 68, 95, 99.7% empirical rule, which applies to bell-shaped distributions specifically, or approximately bell-shaped or normal-shaped distributions. That's next time.